In this video, we are going to talk about heterogeneous equilibria. If we have homogeneous equilibria, we also have heterogeneous equilibria, in which the reactants and products are present in more than one phase. Okay, unlike in homogeneous equilibria, wherein all the substances, the reactants or products, are present in one phase, in a heterogeneous equilibria, you can find at least two different phases. And these phases may include pure solids and liquids. Okay, our question is, how are we going to write the equilibrium expression for heterogeneous equilibria? Is that the same with how we write the expression for homogeneous equilibria, particularly with the gases? Because so far, what we dealt with is the homogeneous equilibria for equations involving gaseous substances. So would it be the same? The answer to that question is no, it's not. Why? Because when you write for the equilibrium expression for heterogeneous equilibria, you are not going to include pure solids and liquids. For what reason? For the reason that concentrations of pure solids and liquids are fixed by their density and molar mass and do not vary with the amount, because density is an intrinsic property. It does not vary with the amount, and molar mass is also constant for a certain substance. Okay. Of course, you only have 1 molar mass for a specific substance like carbon dioxide, for example, or for calcium carbonate, for example. You have a specific molar mass. Molar mass does not vary, as simple as that. So if the concentration of pure solids and liquids are fixed by this quantities which do not vary, then it follows that the concentration does not also vary for solids and liquids. Okay, just like this one. Because you have here the solution for calculating the molar concentration of a certain solid, for example. So you have here density, gram per ml divided by the molar mass. So as you can see here, you have the molar concentration, and it shows here that the concentration of a certain solid is fixed by their density and molar mass. So that is why the concentrations of solids and liquids are incorporated in the K sub C value, but not part of the variable Kc expression. Okay, so if given this case, calcium carbonate decomposes to calcium oxide and carbon dioxide, what is the equilibrium expression for this? So you can see here, you have calcium carbonate in solid form and calcium oxide in solid form and carbon dioxide in gaseous form. So obviously this is a heterogeneous equilibrium, okay, because you can see here at least two phases. Okay, so what is the equilibrium expression for this? As stated earlier, you are not going to include in the expression the concentration of pure solids. Okay, as as those quantities do not vary. So our expression for that is just K sub C is equal to the concentration of carbon dioxide. So as simple as that. Okay? How about this one? Write the equilibrium expression for the following reaction. So you have here 3 moles of copper, solid copper, plus 2 moles of aqueous nitrate. So when we say aqueous, this is in solution with water, meaning the solute here is being dissolved in water. And then you have hydrogen, 8 moles of aqueous hydrogen ions forming 3 moles of aqueous copper 2 ions, and 2 moles of nitrogen oxide, and 4 moles of liquid water. So what is the equilibrium expression for this? So we are going to omit pure solid. Do we have pure solid here? Yes, we have. So copper, so this will not be included. And then we also have here pure liquid. So what will be included in the expression are the concentrations of the aqueous substances and the gaseous substances. So for this example, the equilibrium expression is K sub C is equal to the concentration of nitrogen monoxide raised to the power of 2. Then we have for the copper 2 ions raised to the power of 3. Let's change the way we write the ion, and then in the future we will explain what's the difference between plus 2 and 2 plus. That will be discussed in module 4. And then we have, what else we have? Okay, no more in the numerator. Then in the denominator we have concentration of nitrate ion raised to the power of 2 and times the concentration of hydrogen ion raised to the power of 8. So this is the equilibrium expression for this example. Okay, so again, in writing equilibrium expression for heterogeneous equilibria, do not include pure solids and liquids. Only include gaseous substances and aqueous substances, or substances dissolved in water. Okay, we have here modifying equilibrium constant expressions. In other words, what will happen if you change the stoichiometric coefficients of the substances in your equation? Okay, what will happen to the equilibrium constant? Will it change? And if it does, how much would be the change? Okay, so we have here two equations. Let us say that K sub 2, okay, this is just hypothetical. Let us say that the value for K sub 2 is equal to 2. What is the value of K sub 2 if we multiply equation 2 by 4. Okay? Okay, let me write this again. Okay? Okay. At least you can still see here equation 2. So equation 2 is sulfur dioxide plus 1/2 mole of oxygen gas to form 1 mole of sulfur trioxide. Let us say that these are all gases. Okay, these are all gases. Okay. Let us say that the value for K sub 2 is 2. So this is just a hypothetical value. Now, if I am going to multiply this equation by 4, what will happen to your K sub 2? That's the question. What will happen to your K sub 2? Okay. So what do you think? So if you multiply this by 4, so this becomes okay, why 4 moles? Because you use the distributive property, you just multiply 4 by 1 here. There is an understood numerical coefficient here, which is 1. So that is why this is 4. Plus, this becomes 2. 4 times 1/2 is 2. And this becomes 4 also. So what is now the value of your K sub 2? Okay. So let's try to have let us write first the equilibrium expression of the original equation. Okay. The equilibrium expression is K sub 2, since we use K sub 2 here, is equal to the original. This is divided by concentration of times the concentration of oxygen gas raised to the power of 1/2. This is for the original, but what happens here? When you multiply these two, then therefore the power here is also changed. Diba? So it's the same way as you multiply this by the exponent, you raise this whole quantity by 4. Okay? Then if you raise this whole quantity by 4, then you also have to do the same with the term at the left side of the equation. Okay? So, if we are going to substitute this one, then therefore this becomes, your K sub 2 is 2, so raised to the power of 4 is equal to, we have raised to the power of 4 which is consistent with the coefficient here, and then here, using the law of exponent, this is 4 times 1 because you have 1 here. Then this is concentration of sulfur dioxide raised to the power of 4, which is consistent with the numerical coefficient here. And then you have concentration of oxygen gas, 4 times 1/2 is 2. So raised to the power of 2. So in other words, what happens when you multiply the numerical coefficients or the stoichiometric coefficients by 4? You also have to raise the value of k sub 2 by 4. So what happens when you change, when you multiply particularly the equation by a certain number? You raise the value of k sub c, in this case k sub 2, to that power to get the new value of the equilibrium constant. Okay? So that's the case there. Okay, how about if we multiply equation 1 by 2? Okay, what is our equation 1? Let's copy equation 1. We have equation 1 is, we have 2 moles of sulfur dioxide plus 1 mole of oxygen gas to form 2 moles of sulfur trioxide. So what if you multiply this by, no, not multiply, what if you divide this by 2? What about if you divide this by 2? So kanina ang ginawa natin, we multiply the equation by 4. This time, what about if we will multiply this equation by 2? What about if we divide this equation by 2? What will happen? What do you think will happen to your equilibrium constant? Are you going to raise that the same as we multiply the equation? Or what do you think? Let's try. So if you divide this by 2, the numerical coefficients will be reduced by half. And take note, dividing this whole equation by 2 is just the same as dividing or multiplying the whole equation by 1/2. And let us just say that the value for this is equation 1, k sub 1 is 4, a hypothetical value. So what will happen? So if you multiply this by 1/2, then what will happen to your equilibrium expression? So let us write first the original equilibrium expression. Okay, in other words, the equilibrium expression based on the original equation, which is this one. So you have K sub 1 is equal to, okay, the concentration of sulfur trioxide raised to the power of 2 divided by the concentration of sulfur dioxide raised to the power of 2 times the concentration of oxygen gas. So if you multiply this by 1/2, it is just the same with raising this whole quantity to the power of 1/2. This is similar to the previous example, and of course this has to be raised to the power of 1/2. So what will happen? So let's substitute. Your K sub 1 is equal to 4, okay, raised to the power of 1/2. This is equal to, now let's use the law of exponent. So multiply the exponents here. So 1/2 times 2 is 1. So this is concentration of sulfur trioxide raised to the power of 1 divided by the same 1/2 times 2 is 1. So raised to the power of, okay, and then what about this one? This is, okay, raised to the power of 1/2. Okay, I need more space. So what is 4 raised to the power of 1/2? Okay, that is actually equal to 2. That is just similar to square root of 4. So this is 2, and then you have, okay, okay. So what will happen to the value of the equilibrium constant when you divide the equation by 2? So when you divide the equation by 2, you have to get the square of your equilibrium constant. It's the opposite to multiplying the equation by a certain number. Again, if you multiply the equation by a certain number, you have to raise the value of your equilibrium constant to the power of equal to that number. But if you divide, then you have to, for example, if you divide it by 2, then you have to get you have to get the square of the equilibrium constant. If you divide it by 3, then therefore you have to get the cube root of the equilibrium constant. Okay, now how about if we reverse the reaction? So if we reverse the reaction, just like this one, what about if we reverse the reaction? So if you are going to reverse the reaction, what will you do with the K? All you have to do is to get the reciprocal of your K. Why? Okay, let's take this one as our example, the sulfur trioxide. Okay, the original is sulfur trioxide. Okay, this is the case of reversing the reaction. Okay, let me write here. Okay, reversing the reaction. Just refer to the PDF copy of this module. Okay, so let us say that this is the original equation. This is the original equation. You have 2 moles of sulfur dioxide plus to form 2 moles of sulfur trioxide. Now, what is the equilibrium expression for this? The equilibrium expression is K sub C equals square root of concentration of sulfur trioxide raised to the power of 2 divided by the concentration of sulfur dioxide raised to the power of 2 times the concentration of oxygen gas. If you reverse this one, so if you do the reverse, so the reverse equation for this is 2 moles of sulfur trioxide decomposes to 2 moles of sulfur dioxide and 1 mole of oxygen gas. So what is the equilibrium expression for this? Let's use the prime symbol to suggest that we are just reversing the equation. So you have concentration of sulfur dioxide raised to the power of 2 times the concentration of oxygen gas divided by the concentration of sulfur trioxide raised to the power of 2. Now notice that this equilibrium expression, this K sub C prime or K prime sub C, is just the reciprocal of K sub C. So therefore, when you reverse the equation, you just what I'm saying is this K prime sub C is just the reverse of or the reciprocal of K sub C, right? Because if you are going to get the reciprocal of this, the result is this one. So what will happen to the value of equilibrium constant, or what will be the equilibrium constant if you reverse the equation? The value of the equilibrium constant is just the reciprocal of the original value of the equilibrium constant. Okay? Okay. What's the next topic? How about if we have multiple equilibrium reactions? Okay. What is this one? Multiple equilibrium reactions. Now, there are cases in which the reaction happens in mechanisms, in multi-step process. When we say multi-step, meron siyang intermediate reactions and intermediate products na nabuo bago nabuo yung final products. Okay? So, just like in this case, na meron tayong, this is the overall reaction, 4 moles of ammonia plus 3 moles of oxygen gas forming 2 moles of nitrogen gas and 6 moles of water. Now, bago narating itong final products na to, dumaan muna siya sa mini processes. Just like at first, binuo muna yung water and then later, nabuo na lahat ng mga products. So, how are we going to solve for the equilibrium expression for the overall reaction? Of course, pag alam mo ang overall reaction, I mean, pwede mo i-compute base doon ang equilibrium expression. Obviously, diba, alam niyo naman kung paano gagawin yon. But there is another way of solving for the overall K sub C using the values of K sub C for the intermediate processes. In other words, pwede nating i-compute itong overall na K sub C from these values. Okay? Paano gagawin yun? So, all you have to do is to multiply these values to solve for the overall K sub C value. Okay. Now, what is the logic behind that? Bakit kailangan na nating i-multiply? Tama ba na i-multiply lang natin kaagad? Okay? Okay. So, here is the explanation as to why doing such thing is correct. Okay. Consider this reaction. Sorry, we have can I have this? Okay. You have 2 moles of nitrile chloride decomposes to 2 moles of nitrogen dioxide and 1 mole of chlorine gas. Okay, this is our overall reaction. However, it is believed that this reaction happens in 2 mini steps. Okay? Paunti-unti. At first, okay, nitrogen dioxide, okay, and monatomic chlorine gas was formed. And then, after that, ang nangyari, kasi meron tayong 2 moles of nitrile chloride, nag-undergo siya ng further reaction with this intermediate product, okay, your chlorine. At ang nabuo naman niya is nitrogen dioxide and chlorine gas, yung diatomic, no longer the monatomic. So, paano nawala sa overall reaction itong monatomic chlorine? Okay, nawala siya kasi although nabuo siya dito sa step na to, na-consume naman siya sa pangalawang step. Kaya, what appears in the general equation are just these 2 moles of, kasi meron tayong dalawang dito na nabuo, 2 moles of nitrogen dioxide and 1 mole of chlorine gas. Okay? So, meron itong, as you can see here, these mini steps, meron ding equilibrium na nabuo. As you can see here, we have 2 arrows here. Okay? Signifying that we have 2 reactions here, forward and backward reaction. So, meron ding equilibrium na nabuo dito sa steps na to. Okay? So, we will use for the rate of reaction, we will for these mini steps, we will use small values for the equilibrium constant. So, for this one, you have small k sub 1, and then we have k prime sub 1. Okay. K prime because this is referring to the reverse. And then for the second, we have k sub 2, then k prime sub 2. Now, since an equilibrium is established, then therefore the 2 rates, forward and backward reactions are equal. So, remember module 2. The rate of forward reaction is equal to k sub 1 times the reactant NO2Cl. Okay? And the rate of the reverse reaction with respect to these substances, kasi pa-backward siya, so ito naman ang naging reactants for the reverse reaction. So you have K sub 2, sorry, we're using here K prime, not K sub 2, but K prime sub 1 times the concentration of nitrogen dioxide times the concentration of monatomic chlorine. Now, since this is in equilibrium, then therefore we can say that the rate of forward reaction is equal to the rate of the reverse reaction. Kasi nga equilibrium. Okay, substituting, we have K sub 1 times the concentration of nitrile chloride is equal to K prime sub 1 times the concentration of nitrogen dioxide times the concentration of the monatomic chlorine. Okay? Let's rearrange the equation. You have K sub 1 over K prime sub 1 is equal to, we just rearrange the equation. Okay. Okay. So, you know that K sub 1 over K prime sub 1 is just equal to K. Okay? Okay, the ratio of these two values is equal to K. So, therefore, for reaction 1, our K sub 1, since we use subscript here 1 to mean equation 1, so if small k sub 1 is equal to small k prime sub 1, if small k sub 1 over small k prime sub 1 is equal to k sub 1, so therefore k sub 1 is equal to okay, so that's it. So this is our equilibrium expression for the first step. Now how about for the second step? Okay, we will follow the same. Please refer to your copy. Okay, rate of forward reaction is equal to, this time we use small k sub 2 is equal to the concentration of K times, and then the rate of the reverse reaction. Okay, we are now referring to step number 2. You have K prime sub 2 times the concentration of nitrogen dioxide times the concentration of now substituting, since this is equilibrium, so rate of forward reaction is equal to the rate of the reverse reaction. So substitute rate of forward reaction is equal to the rate of the reverse reaction and then let's rearrange the equation. So we have small k is equal to the concentration of and then, so what you have said, small k over small k is capital K. Dividing these two values will result to a single quantity called equilibrium constant. That's it. That's the explanation. So since this is referring to the second step, so we use subscript 2. Okay. Okay. So, what are we going to do now? We will solve for the K sub C. Now, K sub C is equal to the products of K sub 1 and K sub 2. So if you're going to substitute the values, so you have, what is our K sub 1? You have, okay, it's found above. So when you watch this video, kindly write, take down notes as you watch the video to be able to follow. Okay, so this is our K sub 1 times or K sub 2, which is this one. Let's just copy that one. Okay, tama ba? Tama naman. Then we have okay. Then we will cancel out this one. I think it's better if we use different color. Not this one. Okay. Bakit cancel siya? Kasi nga, na-produce siya, this is a product of the first step, but it is consumed in the second step. Kaya hindi na natin siya makikita sa final products. Wala siya doon sa final products. Okay. So we have here okay. Okay. Notice that this equation, this expression will be derived if we write the equilibrium expression of the equilibrium expression of the overall reaction. Okay. Where is it? Sorry, this one. Alright? So as what I have said earlier, that we can derive the expression for this overall reaction from the intermediate steps. Okay. Now, ibig sabihin na tama pala, diba kanina, tama pala na i-multiply natin ang given equilibrium constants for the many steps in order to get the equilibrium constant of the overall reaction. Okay?